So we are going to do this topic, Ampere's circuital law. So let's go through the definition first. So what is Ampere's circuital law? Now, Ampere's circuital law states that the line integral of the magnetic field around any closed circuit is equal to mu naught times, that is mu naught is the permeability, times the total current I threading or passing through this closed circuit. So mathematically, it would mean that B dot dl line integral of the magnetic field around will be is equal to mu naught times the current that is passing through this closed circuit. Now, what does it means? It means that if you have a current, okay, if you have a current, and if you make a closed loop around it, okay, this closed loop can be anything. It can be anything. You can make a closed loop like this. You can make a closed loop like this. Okay, any kind of closed loop. But it is always apt, or it is always useful to make a closed loop like this, so that the loop is also in the same direction or the same shape of the magnetic field, circular magnetic field. So it will be more useful if you have a loop which will be in the shape of the magnetic field itself. But it is not necessary. You can have any kind of loop around it. Now, this loop is also called Amperian loop. Amperian loop. So as in the electrostatics, you had Gauss's law and you have Gaussian surface. So the Gaussian surface was enclosing some charge, and that's how the Gaussian theorem worked. So here also there's this is the Amperian loop, and this Amperian loop is enclosing this current. As you can see, this Amperian loop is enclosing this current. So if you do the magnetic field dot product with this dl component of this Amperian loop, so what will you get? You get mu naught times the current which is enclosed by this loop. Okay, we'll get the current which is enclosed by this loop. So now this particular Ampere circuital law can be visualized in a variety of different ways. So one of the ways is like this. So for example, if you have a loop, okay, if you have a loop and you have multiple current passing through the loop like this. So as you can see here, there is multiple current passing through the loop. Okay, this is your Amperian loop. Okay, this is the Amperian loop, and you have multiple current. So you have a current which is I1 going in the upward direction. Okay, then you have I2, I3 current. So I2 is also going in the upward direction, and I3, as you can see, it is going in the downward direction. Okay, so the upward current would be taken as positive, the downward current is taken as negative. In this case, your expression for Ampere circuital law expression would become something like this. Okay, it will become something like this. So B dot dl here, B dot dl will be is equal to I1. I1 will be in positive because it's going in the upward direction, plus I2, and minus of I3 because I3 going in the downward direction. Now, again, as I told you that you can take any Amperian loop. Okay, it is not necessary that you have to take the Amperian loop always as a circular in the shape of the magnetic field lines. But it is again useful to take in the shape of magnetic field lines. So here we see that we have an Amperian loop. Okay, we have an Amperian loop and we have multiple current which is going up or down. 1, 2, 3, 4, 4 currents we have, current going up and down. So in this we can very well see that the current I1 is going up. Okay, it is going up in the upward direction. I2 is going in the downward direction. I3 is going in the upward direction, and I4 is also in the upward direction. So we can see that I1, I2, I1, I3, and I4 will be positive values, and I2 will be a negative value because it is going down here. So again, my Amperial equation will become B dot dl is equal to mu naught I1 plus I3 plus I4 minus of I2. Very simple. Now, next is the application of this Ampere circuit law. So where do we apply this? Okay, so first we are going to apply this Ampere circuit law in a case of an infinite long conductor. Okay, infinite long conductor. So we have already done derivations related to infinite long conductor, and just for the reminder, this was our derivation, the infinite long conductor. you would come to mu naught I by 4 pi a. A would be the distance at which you want to find the magnetic field, and this will become sine of sine phi 2 plus sine phi 1. So this was our expression for the infinite. This for the infinite wire, this phi 2 is equal to phi 1 is equal to 90, and that is why you were getting mu naught I by 2 pi a. Okay, just for the reminder. So we are going to use again, we are going to find the magnetic field using the Ampere circuital law. I hope you all remember that Gauss's theorem also had a similar analogy, that Gauss's theorem was mainly used to find electric fields. So Ampere's circuital law is also used to find magnetic field. Okay, Gauss's theorem is to used to find electric fields, and Ampere circuital will be used to find magnetic field. So here we have, this is our current carrying conductor. Okay, this is the current carrying conductor, and this is an infinite conductor. And here we have this as our Amperian loop. Look very closely. This is your Amperian loop. And here the Amperian loop is also in the same pattern as the magnetic field line. So when you do this integration B dot dl, so you will find that the dl component of this Amperian loop, the dl component of this Amperian loop, and the direction of the magnetic field is in the same. They have the same direction, the dl component and the magnetic field is in the same direction, and as they are in the same direction, so their angle theta would always become 0 degree, and cos of 0 will be always 1. So that is why B dot dl, the calculation would be very simple. So B dot dl is equal to, again, what? Mu naught times the current enclosed. So this was our Ampere circuital law. And if we integrate this dl, okay, if we integrate this dl, so what do we get? So if we integrate this dl, we will get the circumference, that is 2 pi a or 2 pi r, in this case 2 pi r. So what do we get? B into 2 pi r is equal to mu naught times I, or simply B is equal to mu naught I by 2 pi r. So you see, we get the same expression. We get the same expression as we have got from the Biot-Savart. Okay, from the Biot-Savart also we got the same expression, and from the Ampere circuital law also we got the same expression for the magnetic field here, mu naught I by 2 pi r. So this derivation is very simple, and it is also important for all your PU and CBSE level exams. Okay. Next, we move to finding the magnetic field inside a solenoid. Okay, a straight solenoid. Now, what is a solenoid? So let's see what a solenoid looks like. Now, first you have to visualize how the solenoid looks like and where is the magnetic field. This is very important. So take your time and draw the figures if you want to. This is our solenoid, which is also an electromagnet. You have done electromagnets in your junior classes. So look at this diagram carefully. In this diagram, you can see that this is the current conductor. Okay, the current conductor being wound up like this. Okay, these are the current conductors. So the current is flowing in this direction. Okay, these are the current conductors, and due to this current conductor, you have some magnetic field. We have already understood that a circular current is going to produce a magnetic field. We have already done that. So if you have multiple circular loops like this, they are going to produce even more stronger magnetic field. Okay, we have already done that. So this is a solenoid, and it is going to produce a very strong magnetic field. Now the direction of the magnetic field is from here. You can see this is the direction of the magnetic field. So this is our north end, and this is our south end. Okay, so magnetic field outside this solenoid is moving from the south back to from the north to the south. Sorry, from the north to the south, and within the solenoid, inside the solenoid, it is moving from the south to north. Okay, so it's very important to understand very basic NCERT level concept that magnetic field line moves from north to south outside the magnet, but from south to north inside the magnet. Okay. Again, you also have to observe here that within this region, okay, within this region, if you see that the magnetic field line is almost parallel, okay, they are almost parallel, okay. So we can conclude that right at the center of the solenoid, okay, right at the center of the solenoid, this magnetic field line becomes almost parallel, okay. at the center of the solenoid. So this is how a solenoid looks like. Now, magnetic field of a solenoid looks like this. Magnetic field of the solenoid looks like this. Hold on. So here you can see this magnetic field line, as we have already discussed, moving from the north to the south outside the magnet, and from south to the north inside the magnet. And within this region, the magnetic field line is almost parallel. Right at the center, it is almost parallel. Okay. These cross and dot, as you can see here, is the direction of the current. So please don't confuse it with the magnetic field. As I told you many times before, that cross and dot are method to represent direction into the plane and outside the plane. So a dot here would means that the current is coming out, and a cross means that the current is going in here. Okay, so this is what it means. Don't confuse it with the magnetic field. So this is how a magnetic field line due to a solenoid looks like. Okay. Now, this particular derivation, the derivation for finding the magnetic field strength, of a solenoid, this derivation is very simple for the PU and CBSE level, but this particular derivation is not very useful for any competitive exam. For the competitive level, you will not be using this particular derivation or any logic behind it. I will tell you what exactly you have to use. So let's go through this derivation and keep in mind that this is only useful for your PU and CBSE level derivations. Okay, so in the PU exam, if this derivation comes, or in the CBSE, ISE exam, then it is useful. But for competitive level, this derivation has no particular value as such, because most of the time you will not be using the logic used in this particular derivation. Now, look at this diagram very carefully, because this is what you have to draw in your board exam. You have to draw this. First, see this part here. You can see these dots here. So these dot represents the current which is coming out of the plane, and here you can see these cross would represent current which is going into the plane. So it means that the current is actually coming out like this and going into the plane. So this is what the direction of the current is. Okay, this is how the direction of the current is, and we have just now understood that within the solenoid, right at the center of the solenoid, the magnetic field is almost parallel to each other, isn't it? We have just understood the magnetic field is almost parallel to each other. So this is our parallel magnetic field line. Okay, you can see this is our parallel magnetic field line here. So we are going to take a Amperian loop here. Okay, we are going to take an Amperian loop, and our Amperian loop is A, B, C, D, A. So this is our Amperian loop. So in our Amperian loop, we can very well see that this loop has four segments. Okay, the segment A to B, B to C, C to D, and D to A. There are four segments of this Amperian loop, and we are going to solve each segment individually. Solve each segment individually means we are going to consider individual integration of each of these segments. Now, individual integration of each segment would mean that B dot DL, when you do, you will have to do B dot DL for A to B, then B to C, C to D, and D to A. Okay. So B dot DL will become integration of A to B, B dot DL, then B to C, B dot DL, C to D, and D to A. Now, look at the figure once again. You will find that B dot DL for this segment BC. Okay, look at this segment here, BC. So this segment, as you can see, the current is in this direction. So our DL, that is the current element, will also be in the same direction, in this direction, and our magnetic field is in this direction. So it is 90 degrees. Okay, dot product of any two vectors which are 90 degrees will be is equal to 0. So we will find that BC, this value integration of B dot DL for BC segment will become 0. So this here BC segment this one will become 0. The same is going to happen with the DA segment again, because DA segment is also in this direction and magnetic field in this direction. You have 90 degrees angle here, and that would means DA segment here also will become 0. These two segments become 0. Then what will happen to CD, the segment C to D? Now C to D is outside the magnet, outside the magnet, and just outside the magnet, the magnetic field is almost is equal to 0. So just outside the magnet, magnetic field is almost is equal to 0 if you find. Then this particular part, BC part, is also then taken as 0. This part is also taken as 0. So the CD part becomes 0, BC part becomes 0, DA also becomes 0, and then we get only to integrate this part here. Okay, we will only integrate integration of A to B, integration of A to B, B dot dl is equal to mu naught times I. Now, A to B, as you can see in the diagram, once again, that A to B represent the length here, this length, the actual length of the solenoid itself. Okay, so the length of the solenoid itself. So if you're going to integrate this small segment AB, so you will end up integrating the total length, the total value. If you integrate AB is a small segment along the axis of this solenoid. So if you integrate AB, so along the axis, if you integrate, you will get the total length. Okay, this is what you'll get, the total length L. Now, if you do integrate this, then what is the total current you are going to take? Now, this becomes a bit confusing. Okay, so be very careful when you are doing this. What is the confusion part here? Because there is something called the number of turns per unit length of the solenoid. So when you do this B dot dl, okay, B dot dl is equal to mu naught times I. I would represent the current. But here in the solenoid, there are many current turns. Okay, there are many the current turns. Okay, many number of current turns. So you would have to take the total number of turns. Okay, you just cannot take one current element because there's a lot of current element here. There's a lot of current turns here. So you have to take all of them. Okay, so number of turns per unit length of the solenoid is small n. Okay, number of turns per unit length is small n. So do remember this as small n. And in some of the study material, some book, total number of turn is written as capital N. Okay, so don't get confused. Small n is always the number of turns per unit length. Okay, number of turns per unit length, and capital N would become this value here, the number of turns per unit length into the length itself, that is the total number of turns. Okay, why? Because why this is important? Because in a lot of numericals, you will find that sometimes the small n value is given, that is number of turns per unit length is given, and sometimes the total number of turns is given. So you have to be very careful in understanding. If the total number of turns is given, then you have to divide it by length to get the small n value, because in the formula you will be using small n value, not the capital N value. Okay, so you will get this as B dot dl will become B into L, that is the total length of the solenoid. We have discussed that if you integrate this dl, you will get the total length of the solenoid, and this will become your mu naught times Ni. Okay, mu naught times n into L into I. Why n into L? Because n is the number of turns per unit length, and L is the total length. So this value is actually capital N. Capital N means the total number of turns. And why are we taking total number of turns? Because we have to take all the current element within that range. Okay, we have to take all the current element within that range. So this here will become n times L. L will cancel from the both side, and B will be is equal to mu naught times Ni. Okay, that's your very simple formula. Go through this derivation again. This is a very common and very popular derivation for board exams. But as I told you earlier, that this derivation is not going to be very useful for any competitive level solution. If you try to solve numerical using this derivation, it won't be of much help. So then you have to use this particular expression. Now look at this particular diagram and this formula. This is a more appropriate appropriate formula or appropriate derivation for this case. So consider this to be the solenoid. Okay, consider this to be the solenoid, and in this solenoid you will find that this is the dot current and cross current. So this is your dot cross. So this is how the current is, and there will be a magnetic field, and the magnetic field at any point in the solenoid, look very closely, a magnetic field at any point in the solenoid you can find, and then you have to join this point with the two ends of the solenoid. When you join this point to the two ends of the solenoid, you will find that they are making an angle beta and alpha with the vertical line. Okay, again, be very careful with what exactly alpha and betas are, because sometime in JJ mains paper, you will find that they would have given you this as an angle of angle and this as an angle. Okay, so be very careful that alpha and beta is the angle which is made by the point to the end, and the angle is made with this vertical line, not the horizontal. Okay, your formula will then become mu naught ni by 2 and sine alpha plus sine beta. If you are going to consider that this is an infinite length, okay, this is also an infinite, both are infinite length, then in that case this alpha and beta both will become 90. Alpha and beta both will become 90, and because these two becomes 90, so again your formula will become mu naught ni. So you will find that this is exactly the formula which we have derived here, mu naught ni. This is the formula we have derived here. So the formula that we have derived is specifically, we have derived the formula that we have derived is specifically for the center. Okay, we have derived for the center, right at the center, what is going to be the value. So as I told you that this particular derivation is only for the board and PU level, because this derivation only derived the value or the expression at the center of the solenoid, considering it's a very long solenoid. So considering it's a very long solenoid, only at the center of the solenoid, this magnetic field is valid. This mu naught ni is valid. But at any other point inside the solenoid, this magnetic field is not there. The magnetic field you need to calculate by using this particular formula. You can also find a magnetic field at one of the end of the solenoid. Considering one end of the solenoid, if you consider, then in that case, one end will be somewhat here, and the other end of the solenoid is considered as infinite. So in that case, your alpha will become 90 and beta will become 0. And this formula of yours, sine alpha and sine beta, so this will become 90 as 1, and this will become 0. So your magnetic field at one end will be half times mu naught ni. Okay, so be very clear that which formula you have to use for all the competitive level questions that will come across in any book, DC Pandey, PM Sharma, whatever you solve. You will have to use this particular formula to finding magnetic field anywhere in the solenoid. And this particular derivation, this formula and this derivation is only useful for board and PU level. Now, solenoid is as such a very good electromagnet, but it has certain limitation. So the limitation of the solenoid is that the solenoid is going to create a very strong magnetic field everywhere around it. Okay, so if you have a solenoid like this, it's going to create a very strong magnetic field. You have a current flowing in this solenoid, and the magnetic field around it will be very strong all around. Okay, everywhere. Yes. So you probably don't need magnetic field at all these regions, or this region, or this region, or this region. You don't need magnetic field at this region, but still the solenoid will end up making a very strong magnetic field. Now, unintended magnetic field is not desirable. That means if you don't need a magnetic field at a particular place and you still have a magnetic field there, so it is going to do some damage. This is good. You are going to learn in next chapter. Okay, electromagnetic induction. You will learn eddy current and all that. Unintended magnetic field will do some damage. So it is not desired that if you desired magnetic field everywhere. Okay, if you don't need a magnetic field at a place, you should not have it. Or else, if there is a magnetic field in that place, it's going to damage other equipment as well. So to overcome this particular limitation of solenoid, a new device similar to the solenoid is made, and it is called toroid. Okay, so this is toroid or toroidal solenoid. So we are going to find a magnetic field for toroidal solenoid. So toroidal solenoid is very simple. It's simply a solenoid which is curled into a circular. Okay, this becomes a circular thing. So let's say you have a solenoid and you just curl it and it becomes a circular thing. And the current is flowing in this direction. So you see this is the current. Okay, this is the current flowing. Okay, so currently this is the current. And the magnetic field for the toroid is limited to this region only. Okay, so the magnetic field of the toroid is limited to this region. There is no magnetic field inside. That is, here magnetic field B is equal to 0, and also here magnetic field also B is equal to 0. So the magnetic field is only within the region of the toroid and nowhere else. So it's a big advantage because it's not going to create any magnetic field at undesired locations. Let's find the magnetic field for this toroid. Now, this is how a toroid looks when you cut the toroid, if you cut the toroid in a horizontal section, so this is how it looks. Okay, if you cut the toroid like this in a horizontal section, it will look like this. So look at this diagram carefully. You can see this cross here and these dots. So again, dot would mean a current which is coming out, cross means that the current which is going in. So this is how the current scheme looks like. This is how the current scheme look like. Okay, and this dot and cross is the current, and then you can see that this here there are three circles. Okay, you can see this is three circles. So this is one circular loop here. This circular loop is within the toroid. Okay, it's in the center of the toroid. There's another circular loop which is inside the toroid, as you can see. This one, this is inside the toroid. Dotted line you can see, and another circular loop here which is outside. Okay, so we have three loops here, loop 1, 2, 3, and it is very well marked. This is how you have to draw in your board exam also. Loop 1, okay, inside the toroid, inside means the center part of the toroid, and number 2 will be inside the toroid, inside the thing, and the third loop is the outside. So we are going to find magnetic fields we are going to find the magnetic field in all these three regions, and for that we will be using Ampere's circuital law. Now, if for the first loop, that is the loop that is inside, okay, for the loop inside, if you consider, then if you consider the loop inside, then you will see that this loop is effectively not enclosing any current. Is it enclosing any current? Look here again. This is your loop, and the current is like this. So effectively, this loop is not enclosing any current. The current is actually coming out from here, going inside here. This loop is not enclosing any current. So if it is not enclosing any current, I is equal to 0. Okay, I is equal to 0. So the length of the loop, you can say 2 pi r, but I is equal to 0. So your magnetic field also becomes 0. So magnetic field at any point P in the open space interior to the toroid is 0. Then magnetic field and the uh, inside the toroid. Okay, magnetic field inside the toroid. So where we can very well see that inside the toroid, if you make this loop, the loop would be enclosing the current. Okay, loop would be enclosing the current. So which loop? Let's find out. This loop I'm talking about, number 2. Okay, this loop. So you will see that this loop is effectively enclosing the current, and which current it is enclosing? It is enclosing these cross currents. Okay, it's enclosing these cross currents. So you can apply Ampere's circuital law here. B into 2 pi r dl, if you integrate, it will become 2 pi r. So B into 2 pi r will become mu naught times Ni. You see, capital N, again, capital N was total number of turns. Okay, capital N is always total number of turns, small n is number of turns per unit length. So here we are going to take N times I, because again there are many current elements. So you have to take all the currents. Okay, all the current, it will become capital Ni. So B will become mu naught Ni by 2 pi r. Capital N by 2 pi r, this value here will become number of turns per unit length. N is the total number of turns, and number of turns per unit length will become small n, that is N by 2 pi r. So N by 2 pi r, N by 2 pi r will become small n. Very simple. And then your expression also looks like this, mu naught Ni. If you are going to find the magnetic field at the loop outside, okay, the outside loop, this loop, okay, you're going to find it for the outside loop. So for the outside loop, you might think that it is enclosing the current. Okay, you might think that this loop is actually enclosing the current. Yes, it is enclosing the current, but if you look closely, we have used that a current upward the plane. So this is the loop, and any current which is upward the plane, if I consider as positive, and a loop into the plane if I consider negative. So here we will see that the net current here become 0. Why? Because if this is the loop, this is your third loop outside, and here we see that this is a current which is coming out dot, but again for equivalent value you have a current which is going down, which is cross. So for this current, if I do plus I, if I this one, if I do minus I, it will cancel out, and so it will cancel out for all the current. It will plus I minus I plus I minus I plus I minus I plus I minus I, and it will cancel out every time, and that is why your net current will become 0. So you see each turn in the toroid passes twice through the area enclosed by the imperial loop 3. but for each turn, the current coming out of the plane is cancelled by the current going into the plane. So I will become 0, and hence B3 will be is equal to 0. So go through these both of these derivations. Both are board level important derivation. You need to draw this diagram to get good marks, or else your marks will be deducted. And you need to write exactly like this: 3 loops and the diagram. The same goes for solenoid also. Same goes for solenoid. Solenoid also, you have to do this derivation. You have to draw this diagram carefully, and this B dot DL A to B and all this you have to do, and you have to also write exactly why they are 0 and so on. But for the solenoid, for competitive level, you have to use this formula. This is a very, very important formula. JEE mains questions has been asked in 2019 and 20 from this particular case. So do remember this formula and all the variation, that is the magnetic field at the one end or at the center or 3/4 length or 1/4 length or whatever it is. Okay. Do also remember that alpha and beta is the angle, which particular angle it is. So in the question, JEE mains question will definitely try to confuse you that alpha and beta is maybe this angle or this angle, or they might not give you alpha beta as it is. They might give you a certain length. Let's say they give you this length or this length, and this length and so on. And then you have to find the alpha beta from there. Okay.